And today I'll be presenting NGAME, which is a lightweight negative mining algorithm that can provably retrieve hard negatives. NGAME has application in multiple domains, and we will be considering extreme classification in particular. The goal in extreme classification is to tag a data point with the most relevant subset of labels from an extremely large label set. Extreme classification allows us to reformulate existing ranking and recommendation problem by treating each item as a separate label. For example, one might want to tag this volley image with the most relevant subset of Wikipedia categories, or perhaps a subset of billions of users that might be interested in finding volley in this image. XC can be leveraged to show personalized ads that are more relevant to the users as they browse the internet. One way to do this is as follows. First, you predict top Bing queries for each web page in user's history, and we typically consider a limited history, and then ads are selected for those queries. In this particular example, the ad is shown for the query book P&O cruise, which was predicted for one of the web pages in user's history. Note that this needs to be done in real time, so the latency of the algorithm needs to be pretty low. In a typical extreme classification, there are two components. First, there is an encoder, E theta, and then there is a classifier W. So, let's take an example. First, the document shift vacations is encoded using the encoder, which is a BERT model in this case, and then classified into 100 million classes using the classifier W. So, we need to learn model parameters, that is theta and W, by minimizing a loss function such as triplet loss. Now, if we note carefully, there are three summation terms in our loss function. First one over the documents, second one over the positive labels of the document, and third one over the negative labels of the documents. Now, in extreme classification, the number of labels can be extremely large, so optimizing this function can be crazy expensive. Fortunately, the number of positives in real-world applications can be around order log L, so that is taken care of. However, we still need to find a way to restrict the number of negative labels so that the training cost can be cut down from linear in number of labels to perhaps logarithmic in number of labels. There are multiple strategies in literature to select those hard negatives so that the training cost can be reduced, and they can be broadly categorized into three groups. The first set of categories selects, draws their negatives either from a uniform or from a unigram distribution. Now, this strategy is quite simple. However, it can also be suboptimal, as the probability of drawing a hard negative at random can be pretty low when your label set is really large. So, let's take an example. In this example, our document is the user search query, best ship vacation with kids, and its positives could be ads related to vacation or ship vacation. Now, a model wouldn't be able to learn much with random negatives such as pineapple, pizza, and things like that. So, we need to come up with good negatives so that a model can learn fast. Second set of approaches falls in batch sampling category. And in batch sampling categories selects the negative out of the positive labels of other documents in the same mini batch. In this particular example, our document is again best ship vacation with kids, and pizza, mobile phone, and watermelon are the positive labels of other documents in the mini batch, and hence they are treated as negatives. Now, variants of in-batch sampling have been demonstrated to yield accurate results, however, with large batch sizes. Unfortunately, processing large batch sizes can be expensive when we are considering transformer style architectures. Finally, ANC style approaches tries to find global hard negatives using the similarity between document and label representations. For example, ANC could find hard negatives such as stilettos and shopping purse for our search query as compared to pizza and watermelon of in-batch sampling. So ANC can come up with really good negatives. However, it can also be expensive, especially when our encoder is expensive as well as our label set is large. So what if we could create our mini batches in such a way that that in-batch sampling could work with moderate batch sizes? That's the key motivation behind our algorithm, which is NGAME. NGAME is a negative mining aware mini batching strategy, and NGAME could yield accurate results, and more importantly, it can do so at the cost which is nearly same as in-batch sampling. In particular, the overhead of executing NGAME algorithm was just 1% as compared to 210% for ANC. Now, ANC create mini batches that contain similar documents. This is achieved by doing the following. First, you cluster the similar documents together and then construct the mini batches out of those clusters instead of using individual data points. So, NGAME could retrieve hard negatives such as stilettos and shopping purse and like that for our search query, batchification with kids. In addition to strong empirical performance, we also present two theoretical results. The first one states that NGAME could retrieve 1 minus order epsilon fraction of hard negatives given an epsilon good clustering and an epsilon good encoder. Secondly, we also show that training using NGAME's hard negatives is guaranteed to converge to an approximate first order stationary point if certain conditions are met. In the XC setting, we train our encoder, that is E theta, and the classifier W in a modular fashion, which is suggested by the DeepXML framework. DeepXML framework allows us to learn accurate models even when the number of labels are in hundreds of millions. So, in particular, in first module, we treat the label embedding, that is EZL, as label classifier and then learn the encoder using the negatives provided by NGAME. So, once the encoder is learned, we reparameterize the classifier as a combination of label embedding, that is EZL, and refinement vector del WL. Finally, we freeze the classifier and learn the refinement vectors del WL using the negatives provided by NGAME. So this is done in a modular fashion in favor of scalability, so that the algorithm can scale to really large real-world applications. In practice, we use distal-BERT encoder as default, since it provides a good balance between accuracy and scalability. One could use different encoders if it suits their application. Moreover, we use a variant of triplet loss to learn the encoder as well as the classifier. Finally, once the training is done, then we learn two nearest neighbor graphs, one over the label embeddings, that is EZL, and second over the classifiers, WL. Given a test point, we query both our graphs and then merge their predictions using a score fusion function F. We consider multiple benchmark datasets, and these are available publicly. The publicly available datasets contain up to 1.3 million labels, and they consider multiple applications like product-to-product recommendation, document tagging, and things like that. Moreover, we also consider a Bing dataset for personalized ad recommendation application that contains 85 million labels. This dataset was created by mining Bing's click logs. In terms of results, NGAME could be up to 8% more accurate than the baseline on the repository datasets, and we consider state-of-the-art deep XC methods to to compare, such as XR transformer, light XML, and attention XML. Moreover, NGAME was also found to be up to 4 times faster at training as compared to these baselines, which allows it to scale to large real-world applications. Talking about real-world applications, we consider two in particular. The first one is personalized ad recommendation, as we discussed earlier. So in this application, NGAME improved the CTR by 23% and improved the click yield by 19% in live A/B testing. And here NGAME was compared against an ensemble of applications in production. Secondly, NGAME improved the quality of predictions by 16% as judged by the human experts. Finally, on the offline datasets with 85 million labels, NGAME improved the precision by 3 to 5% as compared to the baselines. We also consider the application of sponsored search, where NGAME was deployed to show ads in response to user search queries. And here, NGAME improved the click yield by 3% and coverage by 10%. And moreover, it also improved the quality of predictions by 6%. We also try to analyze the impact of negative mining strategy and the architecture on publicly available XC datasets. And here are the results. The first experiment suggests that if we replace our NGAME algorithm with other negative mining strategies such as TAS, DPR, and ANC, then it led to a drop in accuracy, suggesting that NGAME is suited for our applications. Secondly, using larger encoders such as BERT-large led to a minor increase in accuracy. However, the training time increased significantly. Note that the impact of architecture can differ from application to application. In conclusion, we presented NGAME, which is a lightweight negative mining strategy. NGAME can be accurate as well as faster at training on publicly available benchmark datasets. Finally, it provided significant gains in real-world applications of sponsored search and personalized ads. We will be making our code available on this GitHub page. Here's the list of our amazing collaborators from IIT Delhi, UT Austin, IIT Kanpur, and Microsoft. Thank you.